Okay, welcome to the explainer that's basically going to serve as your ultimate cheat sheet for your next geography exam. If you've ever looked up at the sky and wondered exactly how it's structured, or, if you're just staring down a seriously daunting syllabus on atmospheric layers right now, you are in the exact right place. Today, we're going to crack the atmosphere using an analogy I absolutely love, the broken thermostat elevator ride. So grab your notes because we are heading straight to the top. Here is our flight plan for today. We'll start with the wild thermostat, hit the troposphere, the stratosphere, the mesosphere, the upper layers, and finally, we'll lock it all in with a quick test recap. All right, let's jump right into part one, the wild atmospheric thermostat. Okay, let's dive into this. To easily memorize the atmospheric structure without just, rote memorizing a boring list of names, you really just need one core trick. Follow the temperature gauge. See, our atmosphere doesn't just smoothly get colder the higher up you go. Instead, it fluctuates wildly. It goes cold, hot, colder, hottest. Imagine you're stepping into this magical elevator resting right on the Earth's surface, and we're going to ride it straight up into the vacuum of space. As we ascend, we'll pass through 5 distinct zones: the troposphere, the stratosphere, the mesosphere, the thermosphere, and the exosphere. Keep a close eye on the thermostat as we climb.
Moving on to Section 2, Troposphere, the chill zone.
So the doors close and our ascent starts. We're rising from the surface to an average height of about 13 kilometers. Though actually, if you want a great piece of trivia for your exam, it's about 8 kilometers thick at the poles and stretches way up to 18 kilometers at the equator. Now this lowermost layer is the one we're all intimately familiar with, simply because it's where we live. Every cloud you see, every rainstorm, every sudden gust of wind, literally all climate and weather changes take place right here in the thickest, most active part of the atmosphere. And here is the very first rule of our broken thermostat. Just like climbing a snowy mountain, the higher you go in the troposphere, the colder it steadily gets. Specifically, the temperature drops at a pretty precise rate of 1 degree Celsius for every 165 meters you go up. Fun fact, the lowest temperatures in this layer are actually found right over the equator, high up at its absolute peak altitude. As our elevator hits the ceiling of the troposphere, we reach a boundary called the tropopause. This is an absolutely essential transition term you're going to need to know for your test review. It marks the definitive end of our weather-filled zone and the gateway to something entirely different. Next up, Section 3, Stratosphere, the sudden heater. Moving past the tropopause, we extend up to about 50 kilometers above the Earth's surface. And this is exactly where our imaginary elevator's thermostat completely breaks. You'd think getting further from Earth would just make it colder, right? Well, not exactly. First off, the stratosphere is completely free of clouds and weather changes. This calm, super stable environment is exactly why it's the ideal place for flying big commercial airplanes. It helps them bypass all that messy turbulence down below. But the absolutely most crucial feature of the stratosphere is that it contains the maximum concentration of ozone. That's why it's often called the ozonosphere. Now, what's really interesting about this concept is the stark contrast. In the troposphere, the temperature dropped as we climbed, but in the stratosphere, the temperature actually rises. Why? Because that dense layer of ozone is working overtime, absorbing ultraviolet heat from the sun. So the higher we go in this layer, the more heat is absorbed, acting like a sudden, massive heater. We ride this sudden heater all the way up to 50 kilometers, where we hit our second critical test prep boundary, the stratopause. Make sure to take a mental snapshot of this. The stratopause is the ceiling of the stratosphere. And well, hold on your hats, because our elevator is about to take us into a pretty extreme temperature drop. Welcome to Section 4, Mesosphere, the deep freeze. Stretching upward from 50 kilometers to 80 kilometers high, the heater completely fails us here. The temperature once again drops with altitude, plunging us right into the absolute coldest layer in the entire atmosphere. But listen, this deep freeze is actually our ultimate shield. The mesosphere is brutally cold, sure, but it's thick enough to protect Earth by burning up incoming meteorites and even the junk remains of abandoned satellites. All those beautiful shooting stars you see at night, yeah, that's just the mesosphere fart at work, keeping us safe. Moving right along to Section 5, Upper Layers, blazing hot. Leaving the icy depths of the mesosphere behind, we cross the mesopause and transition into the final, upper zones of our atmosphere. In here, our thermostat doesn't just break, it practically explodes. We are now in the thermosphere, located between 80 and 400 kilometers high. This layer contains something incredibly important called the ionosphere, which is divided into sublayers called the D, E, F1, and F2 layers. Because of extreme ultraviolet, X-ray, and gamma radiation up here, the particles are actually electrically charged. This ionization is exactly what allows the thermosphere to reflect radio waves right back down to Earth, which is a real game changer because it makes long-distance communication possible. Just take a look at this mind-blowing number. In the thermosphere, the temperature rapidly increases with height and can actually reach up to 1,500 degrees Celsius. Now, the air up here is incredibly thin, but the tiny amount of gas that is present absorbs massive amounts of high-energy solar radiation. Let's see how this builds into the exosphere. This is it, the final frontier, the absolute uppermost layer of the atmosphere. Stretching from beyond 400 kilometers, way out into the thousands of kilometers, this is where our atmosphere gradually thins out and merges with the vast emptiness of outer space. It's largely home to the lightest gases in existence, things like helium and hydrogen. And the temperature? It just keeps climbing. In the exosphere, temperatures can cross a staggering 5,000 degrees Celsius. I think that definitely cements our ultimate oven analogy for the very top of this atmospheric elevator ride, don't you? All right, let's bring it home with Section 6, your quick test recap. Okay, our elevator has officially reached space, so it's time to consolidate everything for your exam. If you're going to screenshot anything, this is it. So, the crucial point is firmly linking the altitudes with the core traits. You've got the troposphere going up to 13 kilometers, giving us our weather. Then, the stratosphere extends to 50 kilometers, houses the ozone, and gives planes a smooth ride. Next, the mesosphere hits 80 kilometers, freezes over, and burns up meteors. Finally, the thermosphere stretches to 400 kilometers, bounces our radio waves, and gets incredibly hot. And whatever you do, remember the thermostat pattern. Cold, hot, colder, hottest. Before we completely wrap up, I want to offer you one final bonus test fact regarding chemical stratification. If your exam asks how the atmosphere is divided based on its chemical composition, you definitely need to know these two broad layers. Up to 88 kilometers, which covers the troposphere, stratosphere, and mesosphere, the proportion of gases is uniform. We call this the homosphere. But beyond 88 kilometers, up in the thermosphere and beyond, the composition gets non-uniform. We call that the heterosphere. And that just about brings our explainer to a close. But I want to leave you with kind of a provocative physics question. We just saw that the thermosphere hits 1,500 degrees, and the exosphere can cross 5,000 degrees Celsius. So if you were just floating around in the exosphere without a spacesuit, why wouldn't you actually burn up? Well, the answer lies entirely in air density. The air is so incredibly thin up there that even though the individual particles are blazing hot, there simply aren't enough of them colliding with you to actually transfer that heat. It's a wildly counterintuitive fact of atmospheric science. Anyway, I really hope this elevator ride makes your next test an absolute breeze. Keep studying, keep asking questions, and I'll catch you on the next explainer.